In the summer of 1944, while London burned under Hitler's vengeance weapons, a 3-4-year-old engineer named Merle Tuve stared at a device no bigger than a light bulb, a device that every weapons expert in America had declared physically impossible to build. Yet within 6 months, this impossible invention would shoot down 88% of Germany's V-1 flying bombs over Antwerp and fundamentally change aerial warfare forever. This is the story of how scientific stubbornness, wartime desperation, and one engineer's refusal to accept impossible turned the tide against Hitler's terror weapons. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The date was June 13th, 1944. Allied forces had been on French soil for exactly 1 week. The Normandy invasion, the largest amphibious assault in human history, was still a fragile beachhead. Soldiers were dying by the thousands in the hedgerows of France. Every military planner, every general, every strategist was focused on one thing: breaking out of Normandy and pushing toward Germany. And then, at 4:18 inches the morning, everything changed. A strange aircraft crossed the English Channel at 400 miles per hour, faster than any fighter plane of the era. It made a sound unlike anything heard before, a distinctive, rattling pulse that would soon become the most dreaded sound in England. Witnesses described it as a motorcycle in the sky or a flying telegraph pole. It was 27 feet long, carried a 1,870-pound warhead, and had no pilot. At 4:18 a.m., this aircraft's engine suddenly cut out over the London suburb of Grove Road, Bethnal Green. There was a moment of eerie silence, the silence that Londoners would soon learn meant death was falling. Then the explosion. 6 people killed instantly, 9 seriously injured, an entire row of houses reduced to rubble. Hitler's first V-1 flying bomb had struck Britain. Within 24 hours, the trickle became a flood. By June 15th, over 200 volts 1 second had been launched at London. The British called them buzz bombs or doodle bugs, but these nicknames couldn't mask the terror. Unlike conventional bombers, you couldn't negotiate with a V-1, couldn't shoot down its crew, couldn't force it to turn back. It was a robot, a pitiless machine programmed for one purpose: to explode over the world's largest city. Winston Churchill, in his private diaries, would later write that the V-1 campaign represented one of the gravest threats Britain faced in the entire war. Not because of the destruction, the Blitz of 1940–41 had been far worse, but because of the psychological impact. Because these weapons represented something new, something that suggested the future of warfare might belong to whoever could build the most sophisticated machines. By the end of June 1944, the V-2 were falling on London at a rate of 100 per day. The British threw everything they had at the problem. Fighter planes pursued the V-2, trying to catch them before they reached the city. Anti-aircraft guns formed a defensive belt along the coast. Barrage balloons dotted the sky, their cables designed to snag the wings of the flying bombs. And they were failing. The problem was heartbreakingly simple. The V-2 flew too fast and too low for conventional defences. Fighter planes could catch them, but only the newest Spitfires and Tempests had the speed, and even then it was a dangerous game. If you shot down a V-1 too close to the ground, you'd be caught in its explosion. Anti-aircraft guns were even less effective. They were firing shells with timed fuses, trying to predict where a 400 mile-per-hour target would be several seconds in the future. The mathematics of it were brutal. A conventional anti-aircraft shell had to be set to explode at a specific altitude based on the gunner's estimate of the V-1's height and speed. If you were off by even a second, your shell would explode harmlessly in empty air while the V-1 flew past. In those early weeks, it took an average of 2,500 anti-aircraft shells to bring down a single V-1, 2,500 shells. For one target. Do the math. At 100 volts 1 second per day, you'd need 250,000 shells just to stop one day's attacks if your gunners were perfect, which they never were. Britain was hemorrhaging ammunition, and the V-1 second kept coming. On July 6, 1944, Winston Churchill called an emergency meeting of the War Cabinet's Crossbow Committee, the group tasked with countering Hitler's vengeance weapons. The mood in the underground cabinet war rooms was grim. "Gentlemen," Churchill reportedly said, lighting one of his signature cigars, "we are shooting at these infernal machines with weapons designed for the last war. We need something new, or London will be rubble by autumn." One officer, a liaison from the United States Army, cleared his throat. "Prime Minister, there may be something. The Americans have been working on a new type of fuse. They call it a proximity fuse, or VT fuse, variable time. Well, sir, it's rather extraordinary. The shell doesn't need to be timed. It detonates itself when it gets close to the target." Churchill leaned forward. "How close?" "Within 70 feet, sir." There was silence in the room. Then someone accounts differ on who spoke the thought everyone was thinking. "That's impossible. You're talking about putting a radio transmitter and receiver in an artillery shell." The shell experiences 20,000 times the force of gravity when it's fired. It spins at 500 revolutions per second. Nothing that delicate could survive. The liaison nodded. "That's what everyone said, sir. But apparently, one American engineer didn't listen." To understand how the impossible VT fuse came to exist, we need to go back to 1940, before America had even entered the war. Merle Tuve was not a typical weapons designer. Born in 1901 inches, Canton, South Dakota, he was a physicist first and foremost, a man more comfortable with oscilloscopes and vacuum tubes than with bombs and bullets. By 1940, he was the director of the Department of Terrestrial Magnetism at the Carnegie Institution in Washington, D.C., studying cosmic rays and the ionosphere about as far from military work as you could get. But Tuve had been watching Europe burn. He'd seen the newsreels of the Blitz, the footage of London under bombardment. He'd read the reports of how ineffective anti-aircraft fire was against modern bombers, and unlike many of his fellow academics, who believed scientists should remain above the fray of war, Tuve believed that scientific knowledge carried moral obligations. "If we can see a problem," he told a colleague in September 1940, "and we have the ability to solve it, and we do nothing, then we're complicit in every death that follows." The problem Tuve saw was this: anti-aircraft fire in 1940 was almost completely ineffective. Studies showed that it took an average of 20,000 shells to bring down a single enemy bomber. Think about that. 20,000 shells, each one expensive, each one requiring manufacturing capacity, each one requiring a gunner to load and fire for one plane. The reason was the fuse. Every anti-aircraft shell used a time fuse, a mechanical clockwork device that the gunner set before firing, based on their estimate of the target's altitude. The shell would fly up, the clockwork would tick down, and at the preset time, the shell would explode. If the gunner's estimate was perfect, and the bomber hadn't changed altitude or speed, and the atmospheric conditions were exactly as expected, and the shell's clockwork mechanism worked flawlessly, then maybe, just maybe, the explosion would happen close enough to the bomber to damage it. Usually, it didn't. Usually, the shell exploded in empty air, nowhere near the target. Tuve's idea was radical. What if the shell could detect the target itself? What if, instead of a dumb clockwork mechanism, you put a tiny radio inside the presos, shell a radio that would transmit a signal, receive the echo when it bounced off the aircraft, and detonate the shell automatically when the echo showed the plane was within lethal range? When Tuve first proposed this to the Navy's Bureau of Ordnance in October 1940, the response was polite skepticism. "Dr. Tuve," one admiral said, "do you understand the forces involved in firing an artillery shell? We're talking about acceleration forces of 20,000 Gs. That's 20,000 times the force of gravity, hitting the shell in a fraction of a second. We're talking about the shell spinning at 500 revolutions per second to maintain stability in flight. Have you ever seen what happens to a vacuum tube under those conditions?" "It shatters," Tuve admitted. Exactly. And you're proposing to put not just a vacuum tube, but an entire radio transmitter, receiver, amplifier, and detonation circuit into a shell with a battery, and have it survive being fired, survive the spin, survive the flight, and then function perfectly at the critical moment. Tuve, with all due respect, it's impossible. Tuve was quiet for a moment. Then he said something that would define the next 4 years of his life. Impossible is just a word people use when they haven't tried hard enough yet. The Navy didn't give Tuve funding, not at first. But they didn't forbid him from trying either. So Tuve did what stubborn scientists do. He started working on it anyway, using his own laboratory's resources. The challenge was more daunting than even the skeptical admiral had described. A proximity fuse needed to do something that had never been done before. Pack all the components of a radio system into a space about the size of a light bulb, make every component tough enough to survive forces that would pancake a human being, and do it all for a cost low enough that you could manufacture millions of them. And it had to work on the first try. In combat, there are no second chances. Tuve assembled a team of 8 researchers. Most of them were young in their 20s or early 30s because the older, more established scientists thought the project was a waste of time. His core team included a brilliant young physicist named Lawrence Hafstad, an electronics expert named Richard Roberts, and a mechanical engineer named Alexander Ellett. They called themselves, with dark humor, the Suicide Squad, because everyone knew that if they failed, if they wasted time and resources on an impossible project while Britain fought for survival, their careers would be over. The first problem was the vacuum tube. Every radio in 1940 used vacuum tubes, delicate glass bulbs filled with various elements, where electrons would flow in controlled patterns to amplify signals. These tubes were notoriously fragile. Drop a radio off a table, and you'd probably shatter a tube. Now imagine subjecting that tube to 20,000 Gs of force. The team started testing commercial vacuum tubes, firing them in shells on a test range. The results were grimly predictable. Every single tube shattered. Even when they tried reinforcing the tubes, cushioning them, mounting them in special shock-absorbing holders, nothing worked. We went through 500 vacuum tubes in the first 2 months, Lawrence Hafstad would later recall. 500 tubes, 500 failures. Every single one shattered. I remember thinking, maybe the Admiral was right. Maybe this really is impossible. But Tuve had a different perspective. We haven't proven it's impossible, he told his team. We've just proven that 500 approaches don't work. That means we're 500 steps closer to finding the one approach that does. It was in December 1940 that the breakthrough came, and it came from an unexpected place, a light bulb manufacturer. One of Tuve's team members, browsing through industrial catalogues, found a company called Raytheon that made specialized ruggedized tubes for industrial applications. These tubes weren't designed for artillery shells. They were designed for environments with extreme vibration, like mining equipment and industrial drilling machines. Tuve called Raytheon. Within a week, they'd sent over samples of their most durable tubes. The team modified them, reinforcing specific components, changing the internal structure to handle rotational forces as well as linear acceleration. On December 18, 1940, they loaded their first modified tube into a shell and fired it at the Aberdeen Proving Ground test range in Maryland. The shell fired. The tube survived. I remember that moment, Richard Roberts said in a 1965 interview. We retrieved the shell, cracked it open, and the tube was intact. Not just intact, it was still functioning. We hooked it up to a test circuit, and it worked. We all just stood there for a moment, not quite believing it. Then someone, I think it was Merle, said very quietly, "Gentlemen, we just made the impossible possible." But surviving the launch was just the first challenge. Now the team had to make the tube do something useful. A proximity fuse needed 5 main components, all working in perfect harmony. First, a radio transmitter that would send out a continuous signal. Second, a receiver that would pick up the echo of that signal when it bounced off a target. Third, an amplifier that would boost the received signal. Fourth, a discriminator circuit that would determine if the echo indicated the target was within lethal range. Fifth, a detonation circuit that would fire the shell's explosive at the precise right moment. All of this had to fit in a cylinder about 1.5 inches in diameter and 4 inches long. All of it had to operate on a tiny battery. All of it had to survive being fired from a gun, and all of it had to work reliably, because a failure didn't just mean a wasted shell, it could mean a V-1 getting through to kill civilians. The team worked in secret. Even within the Carnegie Institution, only a handful of people knew what they were doing. Security was paramount. If the Germans discovered what America was developing, they'd start working on countermeasures immediately. By March 1941, the team had built their first complete prototype. It was crude, awkward, and barely fit in a 5-inch anti-aircraft shell. But on paper, it should work. The test was scheduled for April 2nd, 1941, at the Dahlgren Naval Proving Ground in Virginia. The target was a drone aircraft, a radio-controlled plane that would fly past at various altitudes while shells equipped with the new proximity fuses were fired at it. Merle Tuve barely slept the night before. 4 years of his life, of his team's lives, would be validated or destroyed in the next few hours. If the fuse worked, it would revolutionize air defense. If it failed, the admirals who'd called it impossible would be proven right. The drone took off at 9:30 a.m. It circled the test range at 5,000 feet. The first shell was loaded. The gun crew, who had no idea what made this shell special, followed their standard procedures. The order was given. Fire. The shell arced upward. Inside it, the tiny radio transmitter began broadcasting. The receiver listened for echoes. The amplifier boosted the incoming signals. The discriminator circuit calculated distances. At 4,800 feet, the shell passed within 70 feet of the drone. The discriminator detected the echo spike. The detonation circuit fired. The shell exploded in a perfect airburst, exactly where it needed to be. Shrapnel tore through the drone's wing. The unmanned aircraft spiraled down and crashed into the Virginia countryside. On the ground, Merle Tuve watched through binoculars. When the explosion happened exactly where it should, he lowered the binoculars slowly. His hands, colleagues noted, were shaking. "It works," he said quietly. "My God, it actually works." The successful test in April 1941 should have been the end of the story. The Navy now had proof that proximity fuses were possible. Production could begin, and American ships would have a weapon that could actually defend against air attack. But this is where the story takes its first dark turn, because having a working prototype and having a weapon you can manufacture by the millions are two entirely different things. The prototype fuses had been hand-built by expert technicians in a laboratory. Each one took approximately 40 hours to assemble. Each one cost about $700, roughly $14,000 in today's money, and they were delicate. Rough handling during transport could knock components out of alignment, rendering the fuse useless. The Navy needed fuses that could be mass-produced in factories by workers with minimal training. They needed fuses that cost perhaps $20 each, not $700. They needed fuses rugged enough to be shipped across oceans, stored in the holds of ships, and loaded into guns by sailors under combat conditions. They needed, in other words, an entirely new industrial process. Tuve's team partnered with manufacturing companies across America. Raytheon, which had supplied the vacuum tubes, became one of the main producers. But they also brought in companies with no military experience. Philco, which made consumer radios, Sylvania, which made light bulbs, Eastman Kodak, which made cameras. The challenge was teaching these companies to build something none of them had ever seen before, while maintaining absolute secrecy about what they were building. Workers at these factories assembled components without knowing what they were for. One person would build the transmitter circuit, another would build the receiver, a third would assemble the detonation mechanism. Only at the final assembly point would all the pieces come together, and even then, many workers didn't know they were building a weapon. "We told them it was a radio altimeter for aircraft," one supervisor later admitted. "It wasn't exactly a lie, it did measure altitude, after a fashion. But we certainly didn't mention that it was going inside artillery shells." By December 1941, when Japan attacked Pearl Harbor and America officially entered the war, production was ramping up, but slowly, painfully slowly. The first production runs were producing about 100 fuses per week, nowhere near the millions that would eventually be needed. And then, in early 1942, disaster struck. A batch of 5,000 fuses, produced at the Raytheon factory, was shipped to the Navy for testing. These weren't hand-built prototypes, they were production models, assembled on the new manufacturing lines. The Navy tested them at sea. The results were catastrophic. 60% of the fuses failed to detonate. The shells either exploded too early, too late, or not at all. 60% failure rate. You can't deploy a weapon with a 60% failure rate. You'd be as likely to endanger your own forces as the enemy. The Navy investigation was swift and brutal. Inspectors descended on the Raytheon factory, taking apart the manufacturing process step by step. What they found was sobering. Tiny variations in the assembly process, a wire soldered at a slightly different angle, a component mounted a few millimeters off-center could cause the fuse to malfunction under the stress of being fired. The tolerances required were far tighter than anyone had realized. We're talking about precision measured in thousandths of an inch, in devices that would be subjected to forces that could bend steel. It was like trying to build a Swiss watch that could survive being hit with a sledgehammer, one engineer said, and then expecting it to keep perfect time afterward. Tuve went back to the drawing board. His team redesigned components, tightened specifications, developed new quality control procedures. They created testing rigs that could simulate the forces of launch without actually firing shells. They trained factory inspectors to spot microscopic defects. By June 1942, the failure rate had dropped to 30%, still too high. By September, it was down to 15%, getting better but not good enough. The pressure was immense. By late 1942, American ships in the Pacific were facing kamikaze attacks. In Europe, the Luftwaffe was still a threat. And everyone in the Navy knew that somewhere in Germany, engineers were probably working on their own version of the proximity fuse, or worse, on weapons that would make current defenses obsolete. The race wasn't just against manufacturing problems, it was against time itself, and against an enemy who never stopped innovating. In November 1942, the Navy made a fateful decision: deploy the VT fuses in combat, despite the imperfect reliability. The reasoning was coldly logical. Even a fuse with a 15% failure rate was better than conventional fuses that missed 95% of the time. The first combat use of the VT fuse came in January 1943 in the South Pacific. The cruiser USS Helena, equipped with VT-fused shells, engaged Japanese aircraft during the Battle of Rennell Island. The results were dramatic. The Helena shot down several aircraft with a fraction of the ammunition previously required. But the Navy imposed strict restrictions. VT fuses could only be used over water, where duds would sink rather than potentially falling into enemy hands. The technology was too valuable to risk capture, and so, through 1,943, VT fuses slowly proved themselves in naval combat. Failure rates continued to drop as manufacturing improved. By early 1944, production had ramped up to 40,000 fuses per day. The weapon that had once been impossible was now rolling off assembly lines across America. But the VT fuse's greatest test, the challenge that would justify every hour of work, every setback, every sleepless night, was still ahead. Because in June 1944, Hitler's revenge weapons began falling on London, and Britain was about to discover that sometimes the difference between survival and destruction is an invention that everyone said couldn't be built. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By August 1944, London had endured 2 months of V-1 attacks. Over 2,400 flying bombs had struck the city. Nearly 6,000 civilians were dead. Another 18,000 were seriously wounded. Entire neighborhoods had been reduced to rubble not from concentrated bombing raids like the Blitz, but from the relentless, random terror of robot weapons that struck without warning, day and night. The psychological toll was worse than the physical destruction. During the Blitz, Londoners had faced human enemies, German bomber crews who could be shot down, who could make mistakes, who might show mercy or be driven back. But the V-2 were different. They were machines, pitiless and inexorable. You couldn't appeal to their humanity because they had none. It was the sound that got to you, one survivor recalled decades later. That puttering engine, like a motorcycle in the sky. As long as you heard it, you were safe. It meant the bomb was still flying. But when the engine cut out, when that terrible silence fell, you knew it was coming down. You had maybe 10 seconds. 10 seconds to find shelter, to pray, to make peace with God. And then the explosion. The British defences were improving, but slowly. Fighter pilots had learned to intercept V-2 before they crossed the coast, tipping them over with their wingtips when they ran out of ammunition, a desperate manoeuvre that required nerves of steel and perfect timing. Anti-aircraft gunners had been relocated to the coast, forming a defensive belt where they could engage the V-2 over open water rather than above populated areas. But the mathematics remained brutal. Even with improved tactics and better positioning, it still took an average of 2,000 shells to bring down a single V-1 using conventional time-fused ammunition. Then, on August 28, 1944, everything changed. That morning, a convoy of American trucks arrived at British anti-aircraft positions along the coast near Dover. The trucks carried wooden crates marked with stenciled warnings. Fragile. Radio equipment. Handle with extreme care. British gunners watched, confused, as American ordnance officers carefully unloaded the crates. Inside each crate were artillery shells that looked almost normal except for the nose cones, which were slightly larger than standard shells and had an odd, translucent quality to them. "What are these, then?" one British sergeant asked an American officer. "VT fuses," the American replied. "Variable time. They're special. Your shells will explode when they get close to the target. You don't have to estimate the altitude anymore." The British sergeant frowned. "How do they know when they're close to the target?" "Magic," the American said with a slight smile. Then, seeing the sergeant's expression, he added, "Radio magic. The shell talks to itself, figures out when it's near something that shouldn't be there, and detonates. I don't pretend to understand how it works. I just know it does." The British were skeptical. They'd been fighting this war for 5 years. They'd seen plenty of wonder weapons that promised miracles and delivered disappointments. But orders were orders. That afternoon, gun crews began loading the VT-fused shells into their 3.7-inch anti-aircraft guns. At 4:47 p.m., radar stations picked up an incoming V-1. The flying bomb was crossing the channel at 390 miles per hour, altitude 2,800 feet, heading directly for central London. A battery of 4 guns near Dover swung into position. In the past, the gunners would have frantically calculated the V-1's altitude, speed, and trajectory, then set their shells' time fuses and hoped for the best. Now, they simply loaded the VT-fused shells and aimed. The first gun fired. The shell arced upward. Inside it, invisible to the naked eye, the tiny radio transmitter began broadcasting its signal at 180 megahertz. The receiver listened. The amplifier boosted incoming echoes. The discriminator circuit calculated distances dozens of times per second. The shell passed 65 feet from the V-1. The discriminator detected the massive echo spike from the flying bomb's metal fuselage. In a fraction of a second, faster than human reflexes could respond, the detonation circuit fired. The explosion created a sphere of shrapnel 150 feet in diameter. The V-1, its fuel tank punctured and its guidance system shredded, tumbled out of the sky and exploded in an empty field 3 miles short of London. 1 shell, 1 kill. The British gun crews stared in disbelief. Then the second V-1 appeared on radar, then a third. By nightfall, the Dover batteries had engaged 12 Vohms second with VT-fused shells. They'd shot down 11 of them. Within a week, every anti-aircraft position along Britain's southern coast had been supplied with VT fuses. The transformation was immediate and dramatic. In the first week of September 1944, British defences engaged 421 volts 1 second. Using VT-fused shells, they destroyed 343 of them before they reached London, an 81% success rate. By mid-September, as gun crews became more experienced with the new fuses and more positions received supplies, the success rate climbed to 87%. And then came the attacks on Antwerp. After the Allies liberated the Belgian port city of Antwerp in early September 1944, Hitler redirected many of his V-1 launch sites to target the city. Antwerp had become crucial to the Allied supply chain. The port handled millions of tons of supplies for the armies advancing into Germany. If Hitler could disrupt operations there, he might slow the Allied advance, buy time for Germany to deploy even more advanced weapons. Between October 1944 and March 1945, Germany launched over 4,800 volts 1 second at Antwerp, more than had been fired at London during the entire V-1 campaign. The Allies deployed their full arsenal of VT-fused anti-aircraft defences around the city. The numbers from those, 6 months. Tell a story that Merle Tuve and his team could scarcely have imagined when they'd started their impossible project 4 years earlier. Of the 4,883 volts 1 second launched at Antwerp, anti-aircraft guns equipped with VT fuses destroyed 4,288 of them. That's an 88% success rate, the number that would become legendary in the history of air defense. Think about what that means. Without VT fuses, using conventional ammunition and tactics, those same guns might have stopped, perhaps 500 of the Vohms second, maybe 10% if the gunners were having a very good day. That would mean 4,383 flying bombs hitting Antwerp, each carrying a ton of high explosives. Instead, fewer than 600 got through. The VT fuse had saved Antwerp from destruction. More importantly, it had saved thousands of lives, not just civilian lives in the city, but the lives of Allied soldiers who depended on supplies flowing through that port. The weapon that everyone had declared impossible had achieved what conventional defences never could. But here's where the story takes an ironic twist, because the effectiveness of the VT fuse nearly caused its greatest vulnerability. Remember, the Navy had imposed strict restrictions on VT fuse use. They could only be fired over water or in situations where duds were virtually certain to be recovered by Allied forces. The reason was simple. If a VT-fused shell fell intact into German hands, their engineers could reverse engineer it, discover how it worked, and develop countermeasures, or worse, develop their own version. The technology's effectiveness made field commanders desperate to use it more widely. After seeing what VT fuses could do against Vohms second, generals wanted them for every anti-aircraft position, wanted them deployed forward with advancing armies, wanted them used against German aircraft wherever they appeared. But Merle Tuve and the Navy's Bureau of Ordnance held firm. One captured fuse could compromise the entire system. The risk was too great. This created bizarre situations where gunners would have access to VT fuses but be forbidden to use them, even as enemy aircraft attacked. Commanders would watch their conventional shells miss targets by hundreds of feet, knowing they had miracle weapons in their magazines that could virtually guarantee hits, but unable to deploy them because of the risk of compromise. The tension came to a head in December 1944, during the Battle of the Bulge. Hitler's surprise offensive through the Ardennes caught Allied forces completely off guard. German forces, supported by the Luftwaffe in its largest operation in months, smashed through American lines. The weather was terrible, heavy cloud cover that grounded Allied aircraft and gave German forces freedom to maneuver. American troops were being overrun, casualties mounted, and German aircraft were attacking supply columns with near impunity because the cloud cover made visual aiming impossible for anti-aircraft guns. On December 19, 1944, General George Patton sent an urgent message to Supreme Headquarters. Request immediate authorization to deploy VT fuses in ground combat against enemy aircraft. Current defensive measures inadequate. Casualties unacceptable. The request sparked a heated debate at the highest levels of Allied command. On one side were field commanders like Patton, arguing that the tactical advantage was worth the risk. On the other were intelligence officers and the scientists who'd developed the VT fuse, arguing that compromising the technology could have strategic consequences far beyond one battle. Eisenhower, as Supreme Allied Commander, made the final decision. On December 22, 1944, he authorized limited use of VT fuses in the Ardennes, but with strict conditions. They could only be used in areas of active combat where the ground was controlled by Allied forces, maximizing the chance of recovering any duds. The impact was immediate. American anti-aircraft batteries, now able to effectively engage, German aircraft, even in poor visibility, began shooting down Luftwaffe planes at an unprecedented rate. The German air advantage evaporated within days, but the risk-takers hadn't counted on German resourcefulness. On December 28, 1944, a VT-fused shell fired by an American anti-aircraft position near Bastogne malfunctioned. Instead of detonating near its target, the fuse failed completely. The shell arced downward and buried itself in frozen ground in an area that German forces would recapture less than 6 hours later. German troops found the shell. They recognized it as American ordnance and, following standard procedure, carefully excavated it for examination. When German engineers opened the shell and saw the radio components inside, they immediately understood what they'd found. This was the legendary American proximity fuse, the weapon that intelligence reports had mentioned, but that no German scientist had yet examined. The shell was rushed to a laboratory at the Luftwaffe testing facility in Rechlin, northeastern Germany. A team of engineers and physicists began the painstaking process of reverse engineering it. What happened next reveals one of the war's great ironies and demonstrates why scientific leadership matters as much as industrial capacity. The German engineers examining the captured VT fuse were brilliant. Within 2 weeks, they'd completely mapped out how it worked. They understood the circuit design, the radio frequency, the detonation mechanism, everything. They sent their report to Hitler's headquarters with a stark conclusion. The American proximity fuse represents a significant technological advantage. However, Germany currently lacks the industrial capacity to produce a comparable device in meaningful quantities. The miniaturized vacuum tubes required are beyond our current manufacturing capabilities. Additionally, the American design reflects a level of quality control in mass production that we cannot replicate under current conditions. In other words, we know how they did it, but we can't do it ourselves. There were several reasons for Germany's inability to respond. First, the bombing campaign against German industry had severely disrupted manufacturing. The precision tooling required to produce miniaturized vacuum tubes had been destroyed or damaged. Second, Germany's electronics industry had taken a different technological path, focusing on different radio frequencies and components that weren't suitable for proximity fuses. Third, and perhaps most importantly, Germany lacked the rare materials needed, particularly certain refined metals and ceramics that America had stockpiled before the war. But the deepest reason was philosophical. German weapons development in the later war years had become obsessed with revolutionary superweapons, the V-2 rocket, jet aircraft, exotic bombs, and missiles. Hitler and his inner circle wanted weapons that would deliver dramatic, war-winning strikes. They wanted spectacle. The VT fuse was not spectacular. It was practical, incremental, an evolution of existing technology rather than a revolution. It made existing weapons better rather than creating entirely new ones. This kind of steady, pragmatic innovation wasn't what the Nazi leadership valued. "We wanted lightning bolts," one captured German weapons designer said after the war. "The Americans settled for better artillery shells, and their better artillery shells beat our lightning bolts." The captured VT fuse did prompt one German countermeasure. They began coating their late-war aircraft and V-weapons with radar-absorbent materials, trying to reduce the echo signature that the VT fuse relied on. But it was too little, too late. By the time these countermeasures were being deployed, Germany had already lost air superiority, and the number of aircraft and V-weapons they could field was dwindling rapidly. Meanwhile, American factories were producing VT fuses at a rate of 40,000 per day. The weapon that had started as an impossible idea in Merle Tuve's laboratory was now the most widely manufactured electronic device in history, more common than radios, more ubiquitous than telephones. But the story of the VT fuse has a darker chapter 1 that wasn't widely discussed until decades after the war. In late 1944, American forces began using VT fuses not just against aircraft, but against ground targets. Artillery shells equipped with VT fuses could be set to detonate at specific heights above the ground, creating deadly airbursts that would spray shrapnel downward over a wide area. This was devastatingly effective against troops in the open, against vehicles, against any target that couldn't hide in deep bunkers. During the Battle of the Bulge, American artillery fired thousands of VT-fused shells in ground attack mode. The effect on German infantry was catastrophic. Soldiers who might have survived conventional artillery by diving into foxholes or shell craters were killed by airbursts that detonated above them, raining shrapnel down from the sky. German prisoners captured after VT fuse bombardments often showed signs of severe psychological trauma. They described the weapons as impossible to escape and like being attacked by the hand of God. Some refused to leave their bunkers even when ordered to advance, so fearful were they of the air-bursting shells. From a purely military perspective, the VT fuse was achieving its purpose. It was saving Allied lives by more effectively destroying enemy forces, but the efficiency was unsettling even to some Allied commanders. One American artillery officer, in a letter home that was later published, wrote, "We fire a salvo of VT shells at an enemy position, and when we advance, we find things I don't want to describe. The weapon is effective terribly, horribly effective. Sometimes I wonder if effectiveness is enough to justify what we're doing." This ethical ambiguity reflected a broader question about technological warfare, a question that would become even more urgent after Hiroshima and Nagasaki. When does a weapon become too effective? When does the ability to kill efficiently cross a moral line? The VT fuse was far less destructive than atomic weapons, but it raised similar questions. It turned artillery from an imprecise area weapon into something approaching a precision instrument of death. It removed the element of chance that had historically allowed some soldiers to survive bombardments through luck or quick reflexes. Merle Tuve, when asked about this after the war, was characteristically blunt. "I made a weapon that kills people more efficiently. I did it to help end a war faster, to save lives in the aggregate by taking lives more effectively in the moment. If that's a moral contradiction, then I'm guilty of it. But I won't apologize for it, because the alternative, letting Hitler's forces kill with impunity, was worse." The full scale of the VT fuse's impact began to emerge. The Navy calculated that VT fuses had increased the effectiveness of anti-aircraft fire by a factor of 5. That means every ship required 1/5 the ammunition to defend itself. Every gun crew was 5 times more likely to stop an incoming threat. In the Pacific Theater, where kamikaze attacks had been devastating to American ships, the VT fuse had saved an estimated 400 vessels from destruction and prevented thousands of casualties. One naval historian later estimated that without the VT fuse, American casualties in the Pacific campaign would have been 50% higher. Against the V-1 flying bombs, the numbers were even more dramatic. Of the approximately 10,000 volts 1 second launched at England and Belgium, Allied defences destroyed nearly 8,000. The vast majority of those kills came from VT-fused anti-aircraft shells. Without the VT fuse, perhaps 7,000 to 8,000 additional VON second would have reached their targets, an additional 14,000 tons of high explosives falling on civilian populations. The British government, in a secret analysis conducted in 1946, concluded that the VT fuse had saved at least 20,000 civilian lives in England alone. But perhaps the most profound impact was psychological. The VT fuse demonstrated that Allied technology could not just match but surpass Axis innovations. After years of German technological superiority, their tanks, their jets, their rockets here, was proof that Allied scientists and engineers could out-innovate their enemies when given resources and freedom to work. Merle Tuve received the Medal for Merit, the highest civilian award given by the US government during World War II. But he was characteristically modest about his achievement. At the award ceremony in 1946, he reportedly said, "I didn't do anything special. I just refused to believe something was impossible until I'd proven it was. And it turned out it wasn't." The VT fuse program had cost approximately $1 billion, about $17 billion in today's dollars. America had produced over 22 million VT fuses by war's end. The factories that made them employed over 70,000 workers. It had been one of the most expensive weapons programs of the war, second only to the Manhattan Project. But unlike the atomic bomb, whose use would be debated for generations, the VT fuse was almost universally regarded as a triumph. It had saved lives, Allied lives certainly, but perhaps even enemy lives by helping to end the war faster. After the war, Merle Tuve returned to civilian scientific research. He never worked on weapons again. He spent the rest of his career studying cosmic rays, Earth's magnetic field, and the fundamental structure of atomic nuclei, the pure research that had been his first love. But the experience of developing the VT fuse had changed him. In a 1950 lecture at Johns Hopkins University, he spoke about what he'd learned. Science isn't just about understanding the world, it's about changing it. And when we change it, we have to think carefully about whether we're making it better or worse. I made a weapon that killed people. I did it because I still believed that stopping Hitler was necessary, and that giving our forces better tools to do that job was right. But I never forgot, not for a single day, that my triumph meant other human beings died. He paused, looking out at the audience of young physics students. Then he said something that would be quoted in textbooks for decades. The real lesson of the proximity fuse isn't about radio circuits or vacuum tubes or weapons design. It's about this. When someone tells you something is impossible, they're really telling you they don't know how to do it yet. Sometimes they're right, it really is impossible. But sometimes, if you're stubborn enough and smart enough and willing to fail 1,000 times to find the one way that works, sometimes you can make the impossible real. And when you do, you'd better be damn sure you're making it real for the right reasons. Tuve died in 1982 at the age of 80. His obituary in the New York Times ran just 4 paragraphs. Most people reading it that day had no idea who he was, no idea that his stubborn refusal to accept impossible had helped win a war and saved thousands of lives. But in defense laboratories and engineering schools, his name was legendary. The VT fuse became a case study in problem solving, in persistence, in the power of incremental innovation. It demonstrated that sometimes the most revolutionary breakthroughs come not from dramatic leaps, but from refusing to quit when everyone says you should. And here, at the end, we come back to the profound irony that makes this story worth telling. The VT fuse was designed to defend against bombers against human pilots in conventional aircraft. It was developed between 1940 and 1943, when the primary air threat facing Allied forces was the Luftwaffe's bomber fleets. But by the time the VT fuse reached its full potential in 1944, the air war had changed. German bomber attacks had diminished. The Luftwaffe was struggling just to maintain air superiority over Germany itself. Instead, The VT fuse found its greatest purpose against a threat that didn't exist when Tuve started his project: unmanned weapons. The V-1 flying bombs were the world's first cruise missiles, the ancestors of the robotic weapons that would define 21st century warfare. A weapon designed for yesterday's war became essential for tomorrow's conflict. Merle Tuve couldn't have predicted this. No one could. But his insistence on solving the fundamental problem how to make a shell detonate near its target without human input created a weapon that was adaptable, that could respond to threats no one had imagined. And perhaps that's the deepest lesson here. In warfare, in technology, in life, the problems you solve today might not be the most important problems you solve. The VT fuse saved lives against V-2, but it also established principles that would guide missile defense, radar systems, and autonomous weapons for generations to come. The man who refused to believe in impossible created something that proved useful in ways he never imagined, against threats he never anticipated, in a future he couldn't predict. In June 1944, as V-2 began falling on London, British anti-aircraft crews were firing 2,500 shells to stop a single robot bomb. By October 1944, using the VT fuse that everyone had called impossible, those same crews were stopping 88% of the V-2 with a fraction of the ammunition. The difference between 4% effectiveness and 88% effectiveness. One engineer who refused to quit when everyone told him his idea couldn't work. Sometimes, the people who change the world are the ones who don't listen when the world tells them to stop trying. Merle Tuve heard impossible and responded with 4 years of work, 1,000 failures, and one stubborn belief that impossible was just a word for not done yet. And he was right. Today, proximity fuses are standard technology in virtually every modern air defense system. The principles Tuve's team developed in the 1,940 seconds using radio waves to detect targets and trigger detonation are still in use, though the electronics have become vastly more sophisticated. Every time a Patriot missile shoots down an incoming threat, every time a naval defense system engages an anti-ship missile, every time any modern weapon autonomously detects and engages a target, there's an echo of that moment in April 1941, when a crude prototype shell detonated near a drone over Virginia, and Merle Tuve's hands shook as he lowered his binoculars. The 22 million VT fuses produced during World War II represented less than 4 years of manufacturing, but they represented something more important. Proof that the word impossible should always be questioned, always be tested, always be challenged by people stubborn enough to try anyway. Hitler's vengeance weapons, the V-2 that were supposed to break British morale and turn the tide of the war instead, became the proving ground for a defensive technology that would save thousands of lives and change warfare forever. The weapon everyone said couldn't be built stopped. The weapons everyone said couldn't be stopped. And it all started because one engineer heard impossible and decided that wasn't good enough. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.